Greetings to our panel. My name is Kishok V Manoharan and my project title is Mixed Mode 1+2 Delamination of Aluminium Joint as a Function of Loading Rate. Before we go to our further slide, I would like to thank our supervisor Dr. Wong Kingjia. Okay, why specifically structural adhesive? We have a 5 major reason why we choose this adhesive. First, eliminate sudden change of stresses. Second, significantly lower stress acting across joint region. Third, uniformly distribute the load. Fourth, increases load carrying capacity. And fifth, eliminate stress concentration. Okay, what are the benefits? Improve handling and acoustic. Second, improve durability. Uh, Third, safety. It's increased energy management capability and enable use of advanced high strength steel. Fourth, cost reduction. Fifth, mass reduction. This is my background, the project background. Adhesive for automotive assembly don't have to be liquid. A variety of adhesive tapes and films are also used in vehicles. For example, a polyamide structural adhesive film from 3M is used to bond rear-view mirror to windshields. And unsupported thermosetting clear films, the adhesive provide high peel, shear and cleavage strength when bonding metal parts to metal, glass or ceramic. The adhesive is reapplied to the metal button that anchor the mirror to the glass. After the adhesive is firmly pressed into place on the glass, it will produce a tough, flexible bond in as little as 30 seconds at 450 Farad. This is my problem statement for the project. Most of the cars designed bonded by plastic clips and nuts which costing and not wearable or fixable after a first heat impact. This make the part easily drop on road and cause accident or major failure. The heat impacted part get loosened and failure on aerodynamics. During aerodynamics, the forces from air causing mixed mode loading like tensile and shear. These are the pictures which I able to collect from internet. Current automobile industries are using this type of clips, and this is what we are going to propose to the industry to change the design for a long-term usage. This is the drag lift downforce from our body flow for your reference. Okay, let's look into the problem statement. Selecting a structural strength adhesive for a specific application require performance criteria of several characteristics. First are bond making properties that determine ease of use and in-place manufacturing cost. First, degree of surface preparation necessary. Second, time to handling strength. Third, cure condition of heat or room temperature, the degree of pressure and the fix to maintain that pressure. Fourth, viscosity for pumping the staying in place after application. Pseudo plastic and thixotropic qualities are desirable so that the adhesive thin during the shearing action of delivery and thicken in place without further shearing. Fifth, application with automated bulk system or handheld applicator to meet varying production requirements. This is my objective of the project, to characterize the mixed mode 1+2 fracture toughness of aluminum joints under different displacement rate. Number 2, to evaluate the fracture mechanism of the adhesive joint at the various loading rate, and to establish the relationship of the mixed mode 1+2 fracture toughness as the function of displacement rate. Okay, here is the scope. What are the materials that we're going to use for this to complete this project? Materials: solid aluminium 6061 plate, 3M film adhesive, delamination test mixed mode 1+2 single leg bonding test, displacement rate 550 and 500 mm per minute, and of course delamination surfaces. Okay, these are the methodology for first half. Step 1, cut aluminium plate AL6061 according to the dimension. Step 2, cut 3M adhesive according to the dimension. Now step 3, grind one surface of the aluminium plates. Step 4, clean or wipe grinded surface by using acetone. Step 5, stick adhesive according to the dimension. Step 6, compress by using hydraulic press. Okay, this is the drawing, specimen drawing for your references, which the length is 200 mm times 3 mm thickness and 120 mm and 3 mm thickness. The red color is the bonding region which we going to use the adhesive. Okay, this is the second half methodology. Mixed mode 1 plus 2 test setup. 1. Fix the 3 mm plate to align the specimen. Number 2. Fix the arm. Number 3. Mark the specimen. Number 4. Place the specimen before we start the test. Okay. Okay, sorry, I'm late. So these are the specimen setup, mixed mode 1 plus 2 test setup, which I mentioned just now. And this is the second half. Repeat it for different specimen and speed 550 500 mm per minute. Calculate the bonding strength, mixed mode 1 plus 2. Surface analysis, you have to identify cohesive or adhesive failure, and then the last is report writing. These are the real test picture which we took in a lab for your references. And this is the real specimen pictures after the delamination test. I segregate into a 3, 5 mm per minute, 50 mm per minute, and 500 mm per minute. Okay, these are the force versus displacement graph which we able to produce after the test. The first picture is 5 mm and the second picture is 50 mm and third picture is 500 mm per minute. Okay, this is the combined picture of all specimen tests. Okay, here we go. These are the discussion. If you see the first graph, the white color pictures graph, this is a back calculated modulus which is GPA versus cross head speed, which is the speed of the cross head, mm per minute, and then the fracture versus fracture toughness, Newton per mm. And on the right, I have included the result we able to produce. I segregate into speed, and then the speed over quasi-static, and then the ln V over quasi-static, and then the average EF and average GT. Average EF is a flexural modulus, and average GT is the mixed mode average mixed mode fracture toughness. On the top of the table, I have included the formula to get this value. When we observe carefully, we can see that the more we increase the speed, the more value is added for the flexural modulus. The more we added the speed, the more we increase the flexural modulus. Same goes to the ln speed over quasi-static, and also V over quasi-static. The more we added the speed, the more the value get added more, increase more. And then when the next we observe, we have to characterize the failure. For 5 mm, the adhesive or interfacial fracture we found. For 50 mm, we found fracture jumping from one interface to other. For 500 mm, the cohesive near the interface fracture. How does it look? I give you another slide, my backup slide. Sorry. These are the possible failure mechanism of adhesive joints we expected. So these are the categories, and then this is how we can conclude what failure is that. And then finally we could assemble, we can gather the critical load and critical displacement, the slope and compliance. These are the value that we got for three different speed, 550 and 500, and the most high critical load is on during the 500 mm per minute, which is 591.86 Newton. And same goes to the critical displacement, that is the highest mm, 12.23 mm, the critical displacement we can measure, we able to measure. And then the highest also the same 500 mm, the slope is 93.67 Newton per mm. And the compliance is almost all same, but the very minimal changes in compliance, Newton per mm, 0.01112, it's like that. Okay, these are the result we got from the end of the test. Okay, the conclusion. In conclusion, this project could characterize the mixed mode 1+2 fracture toughness of aluminium joints under different displacement rate and evaluate the fracture mechanism of the adhesive joint at various loading rates. Besides that, could establish the relationship of the mixed mode 1+2 fracture toughness as a function of displacement rate. Here is my presentation for my project. Thank you for your time, doctor. Thank you for your question later. Thank you so much.